Thank you very much. I'm very happy that you invited me to speak. I'm honored to take part in this distinguished lecture series, and I'm only sorry I can't go to Beijing to be there in person, particularly because I like eating Peking duck. So the talk today is on a rather unusual topic, adversarial examiners and generative models of vision. And this is because over the last few years, I've been worried about the way that we do computer vision, and particularly the way that we evaluate algorithms. And I'm trying to start a small intellectual revolution to persuade people that we ought to be studying algorithms and developing algorithms in different ways. So over the last 5 years or 6 years, there has been enormous progress in computer vision using regression-based techniques like deep networks, evaluated on finite size, balanced, annotated data sets. But in this talk, I will argue that there are limitations to this approach. And the key problem is the space of images is infinitely large and that visual scenes are combinatorially complicated. And I'll describe that in more detail during the first part of the talk. So just I was saying that we have certain methods of evaluating algorithms, and I think they are good but need to be updated and changed, and the talk will be about the rest of that. Okay. So there's no question that deep networks are very effective and innovative. They're far more effective than alternative methods on almost any visual task that can be validated on a fixed finite size test data set. They're also very innovative. New ideas keep happening all the time. Neural architecture search, unsupervised learning, transformer networks and self-attention networks, and neuromodular networks. So, I could give talks on many topics in this area saying how wonderful deep networks are. But I think it's more interesting to talk about the limitations of them and future challenges. So deep networks lack robustness. They lack robustness to adversarial attacks, and these can be both imperceptible attacks and perceptible attacks. Imperceptible means that you cannot tell that the image is being attacked. They're robust to severe occlusions, to significant changes in viewpoint, to context, and to changes of the domain. And I'll now give 5 examples of these. So here are adversarial attacks, imperceptible. So you're taking a limited amount of noise and adding it onto the image. And this was originally done for image classification. My group did it for image segmentation. So instead of seeing two trains here, in fact, you see aeroplanes, and the shape is the logo of the conference. Similarly, over here, you can take an image of a sheep. Below is the real edges that a normal edge detector will have for that image of the sheep. Then you'll add a little bit of extra noise on it, and now the edges become the title of the conference that we submitted this paper to. And other people have done many things that pose estimation. You can add little bits of noise and the algorithms get completely the wrong answer. So these are imperceptible attacks. You can't tell that the image has been changed merely by looking at it. Okay, another one is changes of viewpoint and appearance. So in this case, work done, illustrated by my student Wei Chao, sofa detectors which were trained on ImageNet and would work perfectly on ImageNet, it may not work on unusual viewpoints or on sofas with unusual colors. And that is because these viewpoints and colors did not occur in ImageNet. So to do this, you can take computer graphics, you can model, you can synthesize images of sofas, you can change the color, the material properties, you can change the viewpoint, and you can find certain viewpoints for which the algorithm that's very successful on ImageNet fails to work at all, or gives you results of about 0.1, which are really bad. So they're not robust to changes of viewpoint, and they may not be robust to context changes or occluders. So here are some images made by, well, my ex-student Wei Chi Hang, who just graduated, like Wei Chao just graduated. So you take a monkey and you give it a guitar, and now the deep network thinks that the monkey is a human and also thinks that the guitar is a bird. Similarly, you give a TV set to the penguin, and now the deep network thinks that the penguin is a human. Well, and in this case, it gets the TV set right. The problem is that the objects were occluded, and we assume that the deep network has never seen a monkey with a guitar, but the deep network has seen humans with a guitar, so it makes mistakes because the monkey looks a bit like a human, and similarly for a penguin with a TV set. So deep networks are not robust to these types of situations. Now for patch attacks, and this is work done by Chenlin Yang earlier, well, just published in ECCV this year. I mean, there's quite a lot of literature on patch attacks, but this is just one example that you can do targeted black box attacks on deep networks. So you don't know the architecture of the deep network, you don't know the weights, and you're targeting, so you're trying to turn the object into any specific class, and you can have attack rates which are successful over 90% of the time by putting small patches into the images. So instead of the grille of the car, this little patch means that the deep network thinks it is a bird, a lorikeet. The school bird is also changed into a fire salamander. The folding chair is changed into a snorkel, and the sweatshirt is changed into a pretzel, merely by adding a tiny little patch like this. So that's another form of lack of robustness. The main transfer, this is very general. Here is an image of myself when I was younger, an example of a face. Here is a face made up of fruit. Here is a face which is made up of small humans combined together to form the image of a face, in this case, the face of Ludwig van Beethoven, the famous composer. All these are faces. Any human would look at these and identify them as a face, but it's hard for a computer vision algorithm trained on natural faces to detect these things as faces, etc. And over here, this is a real fish. This is a fish that's been made out of parts of bicycles. And again, getting an algorithm that will take a fish trained on these sorts of fish and get it to work on these artificial fish is not easy at all. And yet humans can do this very, very easily. So deep nets are not robust to these types of situations. Why? And the basic reason is because the test set of images that you have differs from the training set on which you've trained the algorithms. And deep networks, of course, are basically regression methods. They assume that the training and test sets are images which have been sampled from some unknown but underlying distribution. So this is a standard assumption in machine learning. There is mathematical theory, PAC theory, which justifies it. And I think this is, this is the basic assumption that we have for whenever we're evaluating algorithms. But, and so this explains why the deep nets are not robust. This is because they're tested on images that are sampled from a distribution, different distribution than the ones they're trained on. So at first sight, this seems unfair because, you're asking the deep networks to do something that they haven't been trained to do. So, okay, it's a bit unfair. That's true. Now, for imperceptible attacks, the tracking images are very similar to the normal images because they are small perturbations of them. So they come from a distribution that's very similar to the original distribution. But for the other forms of non-robustness, if you have patch attacks or occluders, the images come from distributions which can be very different. Okay, so we say this may seem a little bit unfair to deep networks because you're testing them on data that they haven't really studied. Okay, so you can then ask yourself, is this because the data sets are biased? Maybe a data set that's not biased, all the images that you'll test on will be ones that you've already seen in your training data. So, however, data sets are biased. I've worked in computer vision for a long time now, almost 40 years, and I've never seen a data set that hasn't been biased. And as I'll argue, that's not because computer vision researchers are bad at making data sets. It's because this is inevitable. Now, an example of bias is human performance versus deep networks on ImageNet. So people put up these slides of the performance of algorithms on ImageNet. And so the first two performance levels are before deep networks were used. Performance jumped enormously once you had AlexNet here. And after that, with better and better deep networks, performance goes right down to here. And people show that human performance, or some people claim that human performance is here, which is worse than deep networks. So at first sight, you think, okay, great, deep networks are doing better than humans. But just, wait a minute for that. One of my students, Zotun Zhu, did an experiment to show that deep networks can classify objects on ImageNet without even seeing them and do it much better than humans. So what you do is you take the images here, the images would have objects like birds in them, and you simply put a black patch here. And now you train the network to see if it can classify the black patches. And the deep network isn't perfect, but it predicts that these black patches are birds. Why? Because the deep network has worked on ImageNet, and it knows that in ImageNet, the only objects that can appear in trees are birds. That's reasonable, that's possible. On the other hand, there could be many objects. A human could think there were many objects that could be in a tree. Children could be in a tree, there could be boxes, there could be any number of things in there. A human would have no idea really of what's in the box, in the black box. Bird may be likely, but human would not know at all. So what's happening is really the deep networks are exploiting biases in the data set. Deep nets know that the only objects in trees are birds, but humans don't. And if you try and test humans also on examples from ImageNet, a restricted set of well-known objects, then really human performance is a lot better than as good as deep networks. So deep nets can sometimes do better than humans on objects that humans don't care about. They can recognize plants better than me, but they can't recognize plants better than the gardener. So ImageNet, despite being big, is biased, and the biases can be exploited by deep networks, as this example of classifying the objects without seeing them demonstrates. So data sets are going to be biased. And can we eliminate this type of data set bias? And I'll just ask you to think about trying to do it for the types of, the problems that I mentioned: imperceptible adversarial attacks, changes in viewpoint and appearance, all these other ones. Can we eliminate data set bias by making the data sets big enough so that there were no biases? In which case we could train the algorithm on a balanced annotated data set and then test it, and that would give us reliable performance. Okay, so starting off with imperceptible adversarial attacks. In these cases, the attack images are only slightly different from the real images. They're small changes to the image in the data set. And to some extent, we can fix this bias by making data sets bigger. We replace each data point and image by a sphere of images which are centered on each data point. And we use the min-max strategy that Alexandra Madry at MIT has given a nice sort of theoretical justification for, and essentially use the images that the algorithms has misclassified as training data. So this makes the data set bigger. How much bigger do you have to make it? This is unclear, but in practice, when people do experiments like this, there are now fairly good defenses against these imperceptible adversarial attacks. And so maybe the data set doesn't have to be enormous in order to deal with those attacks. Now think about viewpoint and appearances. And here's a thought experiment that if you use computer graphics to render an image, you take an object, you allow four possible viewpoints, four possible viewpoint parameters: distance, elevation, azimuth, one type of material property, although really an object could have many different types. You allow four lighting conditions and 3 backgrounds. And for all these variables, you allow 1,000 values, and you get too many images. So for a single object, you get 10 to the 39 possible images. And that's enormous. Nobody's got it. Nobody can make a data set that big. Now that's for a single object with only one type of material, and it gets even worse if you consider an articulated object which has p parts which move semi-independently. So for this, we might be able to make data sets that are big enough, possibly, but because maybe with enormous numbers of images, but maybe many of them are very similar, but still this number 10 to the 39 should make you think a little. But if you move on to the other types of non-robustness I was talking about, context, occluders, patches, and different domains, these are exponential. If you take an object like this London bus, you can occlude it by any number of different objects, and suppose you have n possible objects, you have n possible domains, you've got an exponential number of ways of occluding this object. And you can't have a data set that's big enough to represent all those occluders. If you do patch attacks, you could take n possible patches. These are the patches that we used in Chen Lin's random patch attacks method. And to attack an image, you can take these patches, you can select from a dictionary of them, you can place them in a large number of possible locations. And again, you get an exponential number of possible images. So we can't deal with these. We cannot test on all occlusions or all patch attacks with a fixed finite site data set. I mean, maybe this doesn't matter. Maybe if we test with a finite size, that's enough. But personally, I doubt it. And I'll show you examples later on, which I hope will make you doubt it as well. So finite size data sets are not big enough. And the basic assumption that people use in machine learning of using finite size balanced annotated data sets is problematic due to the fact there's a combinatorial complexity of the real world. So we're using the wrong performance measures. so an algorithm does wonderfully well, even on a huge data set like ImageNet, may not be a good algorithm. It may just be a good algorithm for ImageNet, and it may fail badly if it's run, if you test it more seriously. This raises two types of questions. One is, how can we test algorithms if finite sized data sets are not big enough? Two, how can we train algorithms if we only have finite sized training data, and yet we know that the algorithms will be tested on an infinite sized data set? So how to test algorithms? So here is an idea. This is like a sort of a baby step forward done by student Michelle Xu from our group last year. And another point to mention, by the way, is that computer vision should, I would say, care about the worst case and not the average case. Standard performance measures are average case performance. And if you're driving a car like a Tesla, you don't want it to detect pedestrians on average. You want to consider the worst case of how it could fail to detect a human, a pedestrian or something. So the argument, and this is more conceptual at the moment, instead of testing an algorithm by its performance on a random sample of images, which essentially is what we do if we follow machine learning protocols, you allow an adversarial examiner to test a sequence of images where each image is selected based on the algorithm's performance on earlier images. And so this enables the examiner to probe the weakness of the algorithm. The idea here is let your worst enemy test your algorithm. And if you think about this, the way machine learning tests algorithms by just throwing random samples at them is not very intelligent. Would a professor test his students by asking them a randomly selected set of questions? Well, some professors do, but it's not a very good way of testing students' ability. It would be better to ask a sequence of questions where each question you ask could depend on the student's answer to earlier questions. This is similar to the game of 20 questions. So here, what the project was done by Michelle was you did experiments on ShapeNet, which is a dictionary of three-dimensional objects. You used computer graphics, so you could render these objects from different viewpoints, and you try and find the model's weaknesses. Okay, so you want to compare what happens if you do an adversarial examiner compared to just random testing. So random testing, here is one of the objects, and if it's seen from this viewpoint, you get it right 65% of the time. If you see it from this viewpoint, however, you get it right, you never get it right at all because you confuse it with other objects. Now, if you test it just by showing random samples of the object from different views, this is the performance in blue. You don't really realize that there are certain viewpoints for which this object is completely misclassified by the algorithm. On the other hand, the adversarial examiner, and there isn't really time to describe it in detail, creates a dynamic test set of viewpoints instead of a random fixed set. It's only testing on a finite set, but that finite set is chosen by an algorithm which has been learned by using reinforcement learning. And so the adversarial examiner starts off by looking at the object, changing its viewpoint, etc. And after a certain amount of time, it's clever enough to realize that if you start looking at this object from this viewpoint, your performance is really bad. So this is an illustration of it. The patch attacks that Chenlin Wang did were, somewhat similar. You have a deep network, a very advanced deep network that works perfectly if there were no patch attacks at all. You create a texture dictionary of possible patches. You learn a policy using reinforcement learning, which allows you to take patches or sub-parts of patches to put them on the image, creating new images and seeing whether that affects the performance of the network. And these attacks are very successful. They have a success rate of 90% on algorithms that are very successful on ImageNet. So 90% successful attacks with patches that can be as small as this, or maybe a couple of 2 or 3 of them. And also these are black box. You don't need to know anything about the weights of the network you're attacking. And also these are targeted attacks, which is which are also quite hard to do. So just the key idea of the adversarial examiner to say that if you have balanced annotated data sets, these are historically very important and will remain very useful, but they're problematic when faced with the combinatorial complexity of real images, because no fixed finite size data set will be enough to evaluate the algorithms. You can evaluate them on a fixed data set, but you don't know, there's been many other configurations out there. You don't know whether your algorithm will work on those. So if you try something like an adversarial examiner, some strategy like that, it will give you an intelligent way to search for the performance of the algorithm. So again, think about this for a moment. If you take any other form of advanced technology like computer software or cars or airplanes, you do not test their performance by doing a random set of tests on them. You test more intelligently, trying to find their weaknesses and see if they're robust to their weaknesses. And I think for computer vision, we need to start moving towards that type of performance measure. Okay, so for the second part of the talk, I'll now talk a little bit about the second part, which would be how to train algorithms which are robust to these types of situations. So this is to say that even though you've only got finite amount of training data, can you train algorithms that are going to work on infinite amounts of test data that has been chosen by your worst enemy to make them as difficult as possible for you? So for myself, I'll bring in the idea of generative models. So I've been convinced for a very long time, about 30 years, that vision ought to be solved as a form of inverse computer graphics. This is conceptually very attractive. It's been difficult to do this because, particularly 30 years ago, computer graphics was not very good. And there's huge amount of technical problems that you need to deal with. So, but how can I illustrate that this is a promising way forward? And I'll do it by presenting 2 pieces of work that my group has done recently. One which develops generative models which are robust to occluders and to patch attacks, although they've never been trained on occluders and they have not been trained on patch attacks either. Secondly, non-generative models. I have to admit, I'd love these to be generative, and they will be soon, but at least these have been trained using generative models and computer graphics, and which can address domain transfer. So starting off with the first part, how to defend against occluders and patch attacks. So, the idea that actually if you test human performance, humans outperform deep networks significantly when classifying objects which have heavy occlusion. So can we design algorithms which can do better and can perhaps approach human performance? But again, without training them on regular images, without training them on images which have large amounts of occlusion. So here is a paper that was in CVPR this year. And so, why is occlusion important? Well, it's important because it happens all the time in reality, even if it may not happen very often in standard data sets. And these are images from the COCO data set where we deliberately picked examples where the objects are heavily occluded. But as I said, occluders are variable and there's exponential complexity for them. And so vision systems, though trained on finite domains, must be able to generalize to exponentially complex domains. So the claim is deep networks are not robust to severe occlusion. So you don't generalize when you train them with non-occluded data. Now, in a sense, this isn't fair because deep networks are regression methods. They're trained to perform well on data that comes from the same distribution that they've been trained on, and this data doesn't, but still, you know, occlusions happen in the real world. They ought to work in these cases. Okay, so this is a performance. The deep nets are very good if there's no occlusion. As you increase the amount of occlusion, they perform increasingly worse. So as a good deep network researcher, what you should think is, okay, why not just throw in, train with augmented data, train with a whole bunch of things that were occluded. And if you do, you certainly improve performance. You know, you go from 63 for 70% to 80. So you improve performance quite a bit, but you're still not doing very well. And to do this, you had to put in a lot of augmented data. Okay. Now, so here is the idea of what we did. So here is a standard deep network. You have input, you have series of layers, and then you have, and these are convolutional layers which extract features, and then you have a fully connected classification head at the top. So what we do is we keep all the features from the deep network. So we keep the top layer, which has width and height, H and W, has, you know, a set of feature vectors at each point, etc. We keep all this part and we throw away the head. We throw away the classification and we replace it by something else. We replace it by a probabilistic model for the probability of learning the feature vectors here, conditioned on the object that we're looking at, conditioned on the viewpoint of the object. And here are the equations of it. These are partly to say that it's not very complicated. Series of distributions like this. Okay. So this means instead of having a decision process with more weights, instead we have parameters of these probability distributions that we have to learn. Okay, and so here you can represent it like this. So you have the convolutional layers as in the standard deep network. Then you have a process that computes kernels, which we sometimes call visual concepts. Then at the top, we have objects, and for each object, we have several different mixtures, several different viewpoints of it. And then for each object, the output at the end would be to take the object and object viewpoint, which has the maximum score. So the inference for doing this is just very similar to a feed-forward network. The first stages here are completely the same. The second stages are fairly simple, simple calculations, etc. So you can do this really quickly. Okay. You now have interpretable parts, VMF likelihoods of kernels, mixture likelihoods, and also class scores. And Now, at first sight, this looks like a far more complicated thing to learn with a deep network. You know, deep networks, the output is a differentiable function of the input. So this means that you can use, you know, this justifies using backpropagation, which essentially is just differentiation. In this case, we have to do a little bit more than that. The learning involves clustering to get the VMF kernels, which is to find configurations of feature vectors that happen frequently. We also have to do clustering to find different mixtures, different viewpoints. And also we have to train other parameters just by differentiation. But essentially, we just have a loss function overall. We just have to minimize it in a slightly more complex way than just doing backpropagation. But when we're training the algorithm, and this is important, we're not giving it any more information than we give to a standard deep network. We're not telling it the viewpoints. We're not telling it the VMF kernels. These are learned automatically. Okay. So now so far, this is just going to give us a generative model of objects. And this by itself will not be able to deal with occlusion. You know, why should it? Because it's not so different from a standard deep network, except for the top part, which is more interpretable. So, but the advantage of this is it's going to make it very easy to deal with occlusion, because what this model has learned is the viewpoints and the spatial patterns of feature vectors that can occur at the top of the deep network. Okay. And it has, as I say, explainability. The VCM kernels here, learnt by clustering, are similar to parts. So if we look at one of the kernels and see what image patches it likes, we'll find one of them likes the engines of airplanes, another likes the side of airplanes, etc. I have to admit that all the patches aren't as clean as these ones, but these are chosen to illustrate the main idea. So it's got sort of part detectors in here. The class mixtures would correspond to viewpoint or to significant appearances of the object. So for bicycles, this is what happens. You get the bicycle seen from one side, then you get a tandem bicycle that has two people on it as another mixture. Then you get bicycles seen from different angles as a third and fourth mixtures. So what you've got so far, there is a model that's got some interpretability, it's got parts, it's got viewpoints, but it's no more robust than a deep network would be to occluders. But because this is generative, you can introduce occluders into this by allowing for an occluder kernel. So the current model has a process that generates the probability of feature vectors from a model of the object and from a viewpoint. But you can introduce a dummy variable ZPM, P being position, and ZPM meaning being 1, means that the feature vector is generated by the object. ZP being 0 means it's generated instead by the occluder kernels. And so by introducing this additional variable in here, ZP, it gives it a mechanism for deciding if a particular pixel here corresponds to the object or corresponds to an occluder. this is a generative model, and this basic idea is actually quite old. I remember seeing it first in the 1980s, although then it only worked for faces. And indeed, I have a paper in the 90s which also used the idea. But the point is, if you have a generative model for generating data, and you allow, which generates the spatial pattern of the data, and you allow a probability for some of pixels to be generated by something else, you got a mechanism that can deal with occluders. So this variable Z allows you to switch on the occluder process if the feature vectors at a particular point are not generated by the the object model. So what do the occluder kernels like? Well, they like anything that isn't like the object. So they can like feature vectors that come from any sort of images of these type. So you put in occluder kernels, you put in this probability distribution, and this gives you something that doesn't need to be trained on occluders, but is robust to them. And so what happens here, if you take the object with the tree and the bar and the head, what happens is this graph says that dark blue means that the model thinks that the pixels here are generated by the car model seen from the side, and the yellow and the green means that they're generated by the outlier process, i.e. they are occluders. So you start having an algorithm that is not just robust to occluders, but can roughly locate where they are. So similarly, for this image, etc., you are able to localize the occluders while detecting the objects at the same time. You can do this under controlled situations here. You can, classify how well you can obtain localized occluders, etc. So you can quantify that. And then how well are they going to classify the objects compared to the deep nets? Well, here, VGG occlusion is down to 60.3. The comp nets with exactly the same training data are 76.7. ResNet, 71, better than VGG, but the comp net with this additional structure is 78.1, etc. You can do a few other things on here, but still the comp net is far more robust because it has the concept of parts in it, it's learned them, and it knows that some parts of the object can be missing. That's all it needs to know. It doesn't need to know anything about the distribution of the occluders or anything like that, and yet it's robust. This could also be extended to object detection. This was also a CVPR paper. There's a little bit more complication on it. It also means that the compositional nets can roughly locate the boundary of the objects without needing to. That's actually a paper submitted this year, but let me skip over that for time so I can just show you one more slide that we got just recently submitted to CVPR this year. Because if you remember, the patch attacks were very effective on deep networks. So how effective will they be on comp nets? And so if you look over here, if the model is comp nets with VGG background, and here is VGG 16, the accuracy of these models without attacks is very high, but the success rate of the patch attacks on VGG 16 is 98.8. It's completely able to fool the VGG 16, and sparse RS, which is another method that relates to patch attacks, can also make mistakes there, can also cause deep nets to make mistakes. But the comp nets are far more robust, and the attack succeeds, but it exceeds far less often than the time, 12.6% versus 98.8. 0.9% rather than 92.3%. And also the CompNets can sort of essentially roughly detect the patch attacks because again, the attacks are the things that are not explained by the model. Okay, so here is, first example to show that by taking a discriminative deep network and turning it into a generative one, which requires doing a little bit of extra learning, you can, by putting in an outlier process, you can make it robust to these attacks, patch attacks, and to occlusions without even having needed to see an occlusion or to see a patch attack. So this can be very robust and can generalize even from a finite size sample set. So my second example is, I say, the model at the moment isn't generative, but hopefully will be soon. But in any case, it makes use of the idea of having a generative model. So if you imagine, so various people say that you'd like to have algorithms that are trained similar to the way that humans learn. And if you think of a child learning, an infant plays with toys. An infant can have a toy horse or a toy dog. The infant can pick up the toy, it can bend the toy. Here is a toy dog, for example. If you can see this, it can bend it. It knows that the object is articulated at the legs, at the knees, at the head. It could learn that model just by playing with it. You could see it from different viewpoints. You can paint it, you can put different colors on it, etc. So that's the sort of experience that a human infant would have of the world. And if you think what is a good surrogate for it, it's almost that the infant could build a computer graphics model of a horse. And also for the horse, it would be able to know where the joints are, etc. So that is certain motivation that appeals to people like me who are interested in how humans can learn. But how can this apply in practice? So here is work by Wei Chao and Jitang. You take a computer graphics model of a horse or tiger and annotate the key points on it. You annotate the joints. You only annotate one model, one 3D model. From one 3D model, you can generate a very large number of simulated images with the known key points under different lighting, texture, and so on. And then you can train a model for detecting the key points on the simulated images. If you do that, originally it doesn't work terribly well if you try and test it on real images. But if you start off like that and then you retrain it on real images using self-supervised learning, you get a lot better performance. So here is a synthetic horse. So you've annotated this point, this point, this point, this point here in the model. You generate lots of images. You want to find if it can find the key points on this real horse. Okay, so this is really extrapolating learning. You've only got one synthetic model of a horse, and yet you want it to generalize to a large data set of real horses. Okay, you train the model, you train it on fairly unrealistic stimuli. This doesn't seem to matter at all. And instead of possibly trying to get more accurate stimuli, you don't bother. These extra stimuli cost money. I'm too mean to want to pay that money. And so we use a very simple synthetic model, put in a lot of viewpoint diversity, and what does it do? If you just train on the model itself, computer graphics model, you get performance of 25.33, which is not very good. When the real data, if you got the annotations, is 78.9. Data augmentation, however, boosts this up to 60.85. If you put in self-supervised learning, you get up to 70. And so you can say 70.77 is a lot less than the result if you train with the real data, with the real key points, But on the other hand, this is an amazing result since you've got no annotation at all. Only the annotation on your one synthetic horse will take you up to this level. If you care purely about performance, you can take the synthetic model plus the real simulated data, and then you find you do better than just using the real data with the real results. But for me, I don't care so much about that. I really care about this. You can get very good results without any supervision at all, except your computer graphics model. You can do this, you can scale this up to other tasks. I mean, we did this on a horse, we did it on a tiger. You can also try and get it to pass the horse into the head, etc. And this is not as effective as if you had the real data, but it's amazingly effective given that you've only got a limited amount. You've only got one synthetic model of the horse. You can extend to more categories. And one final experiment I asked them to do with not thinking it was succeeding was if you did train it on the computer graphics and then translate it to the natural images, and then you try to run it on these other types of images, pop art, line drawings, you find it actually works fairly well on these. Because what you managed to do in this case is you managed to use synthetic data, and you've also shown that that synthetic data can transfer from computer graphics to real images, and that it can transfer also to line drawings and to pop art without doing any additional work. So this is the end of my second example. And so both my examples are very different from the standard procedure where you have your balanced data sets, you train on one data set, and then you test on the other. That's what machine learning predicts. It's been very successful, but as I'm arguing that I think that's limited because the data sets you have will not be big enough to be representative of the world, and finite sized data sets can never be big enough because of all the complexity due to occlusions and so on and things like that. So improving performance by just testing algorithms in the old, in that old-fashioned way, I think is problematic. And so here, what I'd make is a very big distinction between training and testing. I feel that we ought to move to a situation where you are training the algorithms on a very limited amount of annotated data. I mean, I think training them on large amounts of real data that hasn't been annotated is fine, that's okay. But you ought to be training on small amounts of data where you have the annotations, and yet you need the algorithms to work on infinite amounts of images, including ones that come from very different distributions than the ones that you've trained on. So the testing, if you're only testing on a finite size, your algorithm may well be a very bad one. You don't know because you only know its performance on the finite set, and there's a whole combinatorial set of possibilities that can happen. So for testing, you need to start having a dynamic test set and have a strategy for selecting those images which probe for the weaknesses of the algorithms, rather than just throwing a bunch of random samples at it. For training, I say for myself, I'm a fan of the generative models, and I've only given a little bit of examples of them now, but I think they have the potential to generalize way outside the training data set. And I could give a whole talk about that, but there isn't time for this. But I've illustrated, I think, the generative models, it's easy to make them robust to occluders and adversarial patches. And in ongoing work, we could make them robust to other things as well. Once you start allowing 3D computer graphics in, this means that you can train the algorithms by essentially only annotating the computer graphics models And for each computer graphics model you annotate, you get a very large number of images which you can use for training algorithms, and providing you can solve domain transfer, then those algorithms are going to work on realistic data. So for myself, I'm very excited about these ideas. I hope they're different from the things that you know about in computer vision. And I would say also at the moment that the things I talk about are probably ones that, if you look at the papers that we've done, haven't been, we've only just started, haven't been cited very much. But for that reason, I think that's often a sign that papers are good. The easiest papers to get accepted in a conference are ones that are a little bit better than everything else, because they're not changing your opinion of anything. And in my experience, the papers which are doing things which are fairly new are the ones that often get rejected several times because people don't quite understand the purpose of it. So for myself, I'm trying to persuade you or motivate you to think in this way, to think that, testing algorithms by just finite fixed set can be misleading given the enormous complexity of the world, and that we need better methods for testing. Adversarial examiners are one suggestion, but any method that allows you to effectively search through a very large number of possibilities very efficiently. And for training, we need to have algorithms that can generalize to data that they haven't seen from different distributions. And I argue that generative models are a good candidate for doing that. So that's, I think, the end of my talk. I think I've exactly finished on time. Thank you very much for inviting me to speak. I hope what I've said has been at least stimulating, or at least different from any other computer vision talk that you've heard recently. And for myself, I'm hoping that, for me, I do science because I like exciting ideas. And in my view, exciting ideas often lead to big improvements in the long term. Anyway, so I have a set of afterwards, there's a set of references and things if people want to follow these things up in more detail. But otherwise, I'll stop talking now, and I guess I'll stop sharing the screen, and I can address questions and comments that you may have.